This meeting is being recorded.
Yeah.
Professor Parameswaran, maybe you can take over.
Yeah, thanks. So it's a great pleasure to invite Professor Campana. So actually we knew him about a few meetings that he had visited Tata Institute also twice, and we had been in ICTS, and it's great pleasure in meeting at least online. Can see the face, though we can't see personally. So the Zoom is really made that change, that it's possible to have interactions even from sitting in France and sitting in India. So this has made a revolution. This is really what I would say is a contribution of the COVID-19. So I would like to introduce the first speaker, Professor Frederic Campana from University of Lorraine in France, and he will speak on orbifold curves, geometry, and arithmetics. Please, Professor Campana.
Okay. Thank you. So, okay. Thank you very much. And so it is a pleasure to see you again. Okay. Can we get to the next item? Yes, thank you. Yes, so the topic here, we will consider fibrations between two complex projective and connected manifolds. The meaning of fibration here means just that F is holomorphic, surjective, and has connected fibers. And so, next item, maybe I can go. Yes, one of the fundamental problems in algebraic geometry is to try to deduce the qualitative geometry as given by a certain number of invariants. So, for example, the fundamental group or the Hodge numbers of the Kodaira dimensions and so on, from the ones of B, so the base, and XB, which is the generic and smooth fiber. So I would like to go to the next item. So the objective here of this talk is to say that this is a priori possible only if we take into consideration the multiple fibers of F. Without considering multiple fibers of F, it's usually not completely impossible to read the geometry of X from the geometry of the base and of the generic fiber. So maybe if we can go to the next item. Okay, thank you. Moreover, we have two notions of multiplicity. The classical notion, and I will define it a little bit later, this is not the appropriate one. We will use a different one, and this will lead us, maybe the next item, please. Wait, yes, thank you. We will replace the base B by what we call the orbifold base B and delta of F. And this orbifold base, this is made of B and also a certain orbifold divisor, which is computed from the multiple fibers of F. So the next item, please. Yes. So you can think of B and delta F, so the orbifold base, just as a virtual ramified covering which eliminates the multiple fibers of F by the virtual base change U. And this virtual base change U, it is ramified over the support of the orbifold divisor delta F, and we take the multiplicities of the fibers. They define certain multiplicities on the different irreducible components of the orbifold divisor delta, and you have to take ramification accordingly to this multiplicities. We can move maybe. to the next one. Thank you. Thank you. And so the arithmetic side, the consideration of this orbifold base, B delta F, these pairs, this leads to a conjectural orbifold version of the Mordell long conjecture, among very many things. Maybe we can go to the next item. Thank you. In here, we will restrict to the case where B, so the base, is a curve. This is technically much simpler than the general case, but on the other hand, the ideas are the same as in the case. So maybe you can go to the next page, or I don't know how to. So we will have two versions for this orbifold base. So we take again such a fibration as said, but this time we assume that B is a curve. And so we next go to the next item, please. So now we are looking at the definition of multiplicities. So for each B in B, so this is just a point, since B is a curve, we just take the scheme theoretic fiber of F over B, and so this is just the inverse image of B. This is supported. This is a divisor which is supported on the. This is a divisor on X now, which is made of different components, FK, which are the different divisor which support the inverse image of B. And each is equipped with a certain multiplicity Tk, which is just the vanishing order of F star of B along Fk. So these are the Tks, these are just positive integers. Let me say also that if you take B to be a general point or a generic point on B, then this will be reduced and will have a single component since the fibers are connected. Now, if we can go to the next, now we can define the multiplicities in two ways, either by taking the classical or divisible notion. So we take the GCD of the TKs, which appear here. So we take the largest common divisor of all these positive integers, Tk. Or the second possibility is the next one. This is the non-classical notion of multiplicity. If we can go to the next item. Yes, thank you. Or we can take also MFB without a star this time, and this will be just the infimum of the Tk. This will be in the non-classical infimum notion, and this is the one we will be considering here. So this that MF star of B, this is always a divisor of MF of B, that's multiplicity by looking at the definition. So we can go to the next item. Thank you. So we have this divisibility condition, and it is not always true that we have equality. We shall see some examples later in which we have automatically equality, but also some more difficult examples in which we don't have this equality. If we can go to the next item, please. Thank you. And so we can define now two orbifold bases, B delta F and B delta F star of F, defined as follows. The next item, please. So delta F, now this will be the sum. This will be a rational divisor, a divisor with rational components on B. In fact, this is a certain combinations of the points of B, which are where we have multiple fibers. But now this is defined by the following equality, which is written here. And so you see that you have this 1 minus 1 over MFB, which appears and which are similar to a ramification divisor. And we have, on the other hand, the classical orbifold base, which is defined by delta F star. And this is the same definition, except that we take now the divisible multiplicities. And so this means that in general, we will have a delta F star. This is in each time, this is a finite linear combination because we have only finitely many points where the fibers are not smooth, for example. And so we see that delta F star in general is smaller than delta F, just because this inverse and so on, this is increasing fact. Maybe we can go to the next item. Okay. And now we have now this B delta F and B delta F star, and for each of them we can define a canonical bundle, which is a bundle with rational coefficients. Now this time KB plus delta, and a Kodaira dimension kappa of B and KB plus delta, which is an element of minus infinity, 0 or 1. So how is this defined? I will recall briefly the definition if on the next item, please. So this Kodaira dimension, kappa of B, KB plus delta, this is just defined as the growth order of the integer Nm, which is the number of sections of mkb plus delta of this divisor here, as m goes to plus infinity. Of course, here we have to consider only m which are sufficiently divisible so that this becomes an integral divisor on B. Now I can go to the next one. So we have, in fact, this growth order is like this. We have kappa is minus infinity is n if nm vanishes for each m. Now, kappa is 0 if this nm is bounded, and the last possibility is kappa is 1 if this growth order is linear. Actually, there is another way of computing this, which is much easier, and which is that just by computing the degree of the divisor KB plus delta. Next item, please. Yes. If delta is something is missing here. This is an older, maybe an older thing. So let me say that it can be computed differently. Kappa is minus infinity if the degree of KB plus delta has a certain degree, which you can compute by the formula, which is here, if KB plus delta is negative, or this is 0 if KB plus delta is 0, and this is 1 if KB plus delta is positive. Let me give an example. If KB plus delta is negative, this means that KB is negative itself, because delta has always a positive degree. And so this means that B has to be P1 in this case, and delta is not allowed to be too large. If you want, KB plus delta is 0. There are two possibilities. Either B is an elliptic curve and delta is the 0 divisor, or KB or B is P1 and delta is a certain divisor which has degree exactly 2. And so we shall. It is easy to get some examples. When delta is 0, so if we consider just the case where we have just a B, then kappa is minus infinity, 0, 1. If G of B, the genus of B is 0, 1, or at least 2, respectively. So this is according to the degree of KB also. Yes, something which should be said also here. If the degree of KB plus delta is positive, then you have always a ramified cover of KB plus delta, which is a certain curve B prime, which is of genus at least 2, for example, and which ramifies at order exactly mf of b over each b in a b. So you have this kind of thing. So in some sense, in the case where kb plus delta is a hyperbolic orbifold curve, then you can actually cover it by a really curve of hyperbolic curve, which has genus 2, which is also so we have something which is very precise. We can go to the next. Okay, so I said that in some cases you may have mf of b, for example, if xb is rationally connected. So if you have a fibration x to b to a curve b, and if the smooth fibers are rationally connected, then we have delta f is 0. So this means that you have always above each point always one reduced component in the inverse image of B, of any B. This is a deep theorem, in fact, of Graber, Harris, star. And rationally connected, maybe I will not give the definition, but let me say that it covers in particular the case when the generic fiber is P1 or is projective space or is a Fano manifold, for example, and you have lots and lots of other examples. So these are, in some sense, XB rationally connected. These are the things which look like rational manifolds. Maybe if we can go to the next item. Yes. Now we have the equality that the two multiplicities are always, for any b in the base, they are equal, the classical and non-classical, each time when the smooth fibers of X of the fibration F are abelian varieties. In this case, you have the equality. This is not very difficult. This is an elementary result. But now for the next case, for the next item, now, it may happen that we have delta F is different from delta F star. And this is possible already when the fibers, XB, the generic fiber, is a curve of genus at least 2. But now the construction of such examples is much more difficult, is quite difficult. And I will give an example without making the necessary computations. If you can go to the next. So, for example, there is a famous work, yes, there is a famous work of Kodaira, for example, where he classified the possible elliptic, the degenerate elliptic, the degenerate fibers in elliptic fibrations. This means for surfaces, fibering over a curve and with elliptic smooth fibers. And so in these cases, you can classify the possible things. And Namikawa Ueno in the years 60, beginning of the 60s, classification of the same thing, but for genus 2 curves. And in particular, they got the following example, and the computation now has been made by Lydia Stopino. So I give the example now. If you take Y to P1 cross P1 with the double cover, which is defined in affine coordinates by the equation Y squared, this is T, so the fiber P1 cross P1, these are T and X. And now we have a double cover with equation in affine coordinates. Y squared is T times, and we have X6 plus TX. So what is written here? Yeah. If we equip Y with the projection G on P1, this is the T factor now. This is easy that this is an isotrivial fibration with smooth fibers of genus and two singular fibers over T is 0 and infinity. So, but in general, Y, actually, this is a rational surface, but Y is not smooth. And so we take now the minimal resolution, or X to Y, and so we consider the composed fibration from X to P1, where which is G composed with the resolution R. So now we have two singular fibers, and these two singular fibers, these will have trees of rational curves, and with the non-classical multiplicity over 0 and infinity, this will be 2, but MF star, the classical multiplicity, this will be 1. These fibers actually are simply connected. More precisely, the trees have 6 branches of multiplicities, 2, 4, 6, 3, 3, 2, as shown below. We don't need really to know this, but this is just to show an example and to show that this is not a simple fact. Maybe we can go to the next slide. And so we have, and here we have a drawing of how this fiber looks like, for example. And so each of the things which are colored things, this is a rational curve, a smooth rational curve. And so this, we have a tree of rational curves with the multiplicities which are indicated by colored things. So 2, 4, 3, 3, and 2, and 6. We have 2 and 3. Which appear. So this means that now we have M star is 1, because you have the GCD will be 1. GCD of 2 and 3 will be 1. But on the other hand, if you take the infimum, you will get 2 only. And you see that this example is not an obvious one. This is not a really classical one. And so because of this, we have the possibility of getting really complicated fibers in general. And so maybe we can go to the next slide. And so now I will look to an easy, a very easy example, but which shows you that in fact how double fibers can simple, but classical double fibers may occur. So we start with Y, which is just the product of E and C. E, this is an elliptic curve. And C, this is just a curve of genus 2 and hyperelliptic. Now, and we just look at on the left-hand side, the vertical column. This is G, and we have a fibration from E to C, E cross C to C, and so all fibers are equal to E. So these are elliptic curves. So this is a simple situation. But now we look at an involution on Y, and this involution, this will be on the form T cross H, for example, and this will be a translation of order 2 on E, and H, this will be the hyperelliptic involution on C. And now we take the product, and so this means because T has no fixed points, the involution T cross H from Y to Y, this is a fixed point free involution. And so we look at the quotient Q, which is here, X, this is Y divided by this involution. And so we have here a 2-to-1 étale cover, and everything is smooth. On the other hand, if we take the quotient F here by X, we'll send it to B, which is C divided by H. So we have a commutative diagram here. And so F here from X to B, B is now P1. And so we see that the generic fibers is again elliptic, but we have now what will happen. Of course, the projection P here, this is ramified here. And here, if we look at the fibration on the right-hand side, for example, we see that we have double fibers over each of the 6 branching points Bj of P, for example. And so we have now delta F, this is delta F star, this is an easy computation, and this is 1 minus 1/2 of the sigma of this Bj here. And so if we can look at the next thing, something is missing. So maybe can we get to the thing, because this is an old version and I made it better. Is it possible to go to come back? Sorry. Yes. And here now, if we compute,
maybe if you want, you could. If you want, you could email the latest version. He can share that.
Can you say it again?
If you want, you could email the latest version. He can share that.
Yes, I send you the new version. Later or now?
Now, then they can share. When you're lecturing, he can share the latest version.
I send it. I send it.
Send me.
Edition. Firefox. Okay, yeah. So sorry, I sent it to Devendra.
Yeah, wait a minute. I will be doing it.
Yeah.
Sam, did you receive it?
Yeah. Yeah, I received.
Present that one.
Sorry. Yeah, voilà. Yes. Yes. Do you see? And you have this important relationship here. So that this is exactly, this permits to understand why we have this ramification term, why this delta F has this form. For example, in this case, if you lift the orbifold canonical bundle of B delta F, then what you get, this is exactly the canonical bundle of C, for example. And so in particular, we have the Kodaira dimension of this is 1. So this is again, you can see that this B delta F should really be considered as a hyperelliptic curve, but divided by 2, but in the orbifold sense, if you want. So maybe we can go to the next slide. So now, if since Q y to x, this is an étale double cover with the all important invariants of y and x, they should essentially coincide. So E and C, assume, for example, in the arithmetic side that E and C are defined over Q. Now, in this case, if you map for any K number field, you can f of a set of rational points of y here, of a k rational points of y, they are mapped to c of k, so to rational points of c. And by Faltings, since c is of genus 2, y of k has to be contained in finitely many fibres of g. Chevalier theorem now says that it precisely the arithmetic of y and x, because this is étale cover, so this is exactly the same. You have the same thing which should be true for x. So this means that x of k also this should be is contained in finitely many fibers of f. But this is not immediate now, since if we look at on the right-hand side of the diagram on the previous slide, now the base is just P1. And so you don't get this kind of obstruction for the rational points. This means now that we have to define, in some sense, what are the rational points of the orbifold curve B delta F. And use the fact that this B delta F, this is an orbifold of a general type, a hyperbolic orbifold. And so we just want to see by this, and this is just what I said, but here now the important point is that if I define this putative rational points of the orbifold curve B delta F, if I write these like this, like it has to have the property that the rational points of x of k should be sent to this now. And this should now be in a finite number, because by an orbifold conjecture, which is the orbifold version of a Mordell conjecture, because now we have B delta F is seen as being hyperbolic. Now, before defining these rational points here of this on this orbifold curve, I will look to, because this is easier, to a geometric analogy, but which is important. This is in some sense the same analogy as between the function field version and the arithmetic version. So we are looking at a kind of function field version of this orbifold rational points. Maybe we can go to the next item. Yes. Now, maybe it's better not to write this, but a holomorphic map. So I assume now D, this is the unit disk in C. And I look at holomorphic maps from H from D to B and delta. Now, this is just a holomorphic map from D to B, but with certain additional condition, because a delta is given here. And I will say that this is an orbital morphism if I have the following property, that each time I lift B, some B in B here by H star, so I take the scheme theoretic inverse image of the point B by H. So what I get is a certain divisor of points inside of D, with each of them with certain multiplicities. And so I want that this inverse image here, this scheme theoretic, is at least as large as M delta B times H minus 1 of B. H minus 1 of B, this is the reduced inverse image of. And now M delta of B, this is the multiplicity of B inside delta. So if you want, we have an orbifold here. So this means that each B, or finitely many Bs, if you want in B, have a certain multiplicity which is larger than 1. And so I want this to be larger than times. So this means that if I define, and I always assume that H of D is not contained in delta. So but this is, in this case, this is not a constant map to a certain point of D. And now this means that TH of Z and B is greater than M delta of B for any Z in D, such that h of z is b. And here, what is this th of b and z? This is a certain integer. This is just the multiplicity of z in h star of b. And so I will see it as an intersection number of h of d with b of z. I will make a more geometric version of this. And the definition of an orbital morphism, which is given here, this is motivated by the following example. Now, this is the case in which delta is delta of f. So I consider the situation where f from x to b, this is a fibration of the curve b. And as usual, I take b in b and f star of b, this is what we defined. But now I take this is the infimum of the tks here. And I take h, a small h now, this is something which doesn't go to b, which goes to x, and x is here upstairs. And I consider now the composed map from f composed with h from d to b. So d maps to x, f goes to b, and so I'm composing these two maps, for example, and I get a map from d to b. Now, I will take a b which is such that mf of b is larger, strictly larger than 1, for example, and then it is very easy to see that now the intersection number tfh of z and b, which was defined here in this place, this is larger than f of b because we have f composed with h star of b. This is this sum of tk, and here I have h star of fk. And now, if you want, this means that each time I will have at least, this will be greater than or equal to 1, and this will be greater than or equal to tk. And so this will be greater, certainly, than f of b, because I have here this definition, yes, that this is the infimum of all tks. I'm sorry, this is probably very difficult to follow, but this is easy to see on the blackboard and to understand. But without drawing, this is much more difficult to follow, and I'm sorry. So what is the conclusion? The conclusion is that if I have this f, x and b, and if I take the delta f here, in order to define b, then for any h from d to b, the composed map here will be an orbital morphism for any h. So this is the only important point. And if we look at this, we understand that it is quite natural to define an orbital morphism that way. And we have a functoriality, if you want to write this. If whole of dx, this means just the set of holomorphic maps from d to x. Now, if we compose them with f, we always get morphisms, orbital morphisms from d to b and delta f. So this is the important point. But I will maybe give a graphic interpretation of this. If going to the next slide, please. Yes, and so we have a graphic interpretation. Now I will consider here, let us forget, x, I should not write it this. Yes, okay, yes, this is okay. Let us take b and delta. This is any orbifold curve like this with any orbifold structure, and d, this is a unit disk, and I consider just the recording product.
Has stopped.
Huh?
It said recording stopped. Can you just look at it?
Huh? To cut something? The recording?
Yeah.
The recording is stopped.
Pawan, are you there?
Yeah, we are all here.
Yes, sir.
So why the recording was stopped?
I'm not sure because I'm not using the
Maybe
screen.
you could restart.
Okay.
Pawan? Okay.
This meeting is being recorded.
Okay, continue.
Oh, yes, okay. So I consider here just the product D cross B delta with projection X to D and fibers Z cross B delta, where Z is in D, in the unit disk. Now I write this delta, the delta which is here, in the following form. We have sections of pi here, which are just given the sections Bj. I put them into parentheses. These are just D cross Bj for pi. These are graphs of constant maps, but based on in this delta. And now a holomorphic map H from D to B is identified with its graph, and I put it in with H in parentheses, and this is the set of Z and H of Z for Z in D. The map H now is thus an orbital morphism to B and delta if and only if its graph H, which is this H, intersects each of the sections Bj, which are here. These are these Bj, which are here, with order of contact at least Mj at each point which lies on the graph of the section Bj. Do you see? If you now look at the graphs, then you have a very simple geometric interpretation of what are the orbital morphisms here. And this is now the analogy with the arithmetic case. In the arithmetic case, we will replace D by the spectrum of a ring of integers here, and the product D cross B will be replaced by an arithmetic surface fibered over speak of OS and K. Now, we can go to the next slide if we please. Yes, thank you. So now let B and delta be an orbifold curve just as before. And we assume that this is defined over a number field K. So this means that B is defined over a number field K. And if we want to, you assume that each of the Bj's which appear here are also K rational points of B. And so we have this orbifold here, and OKAS, this is the ring of S integers of K. And now I consider the arithmetic surface, which has as fiber over P, any P, which is in the spectrum of this ring here, the reduction BP of B modulo P. And now I will assume that S is sufficiently large, so this B delta has everywhere good reduction modulo P to modulo any P in spectrum of OFKS. And now any X in B of K
Your voice is gone, Professor.
Yeah, I think we can't hear you.
Probably his network is low or something.
No, I can see his video.
But it is not showing muted.
Yeah. Hello, Campana, can you hear us? No, I think we can't hear you. Just put a chat. His video is there, but audio is not.
We are not able to hear you.
I think he's not able to hear us also. So let's put a chat.
Hello. Maybe you can leave and rejoin again.
Can you hear us?
Can you leave the meeting and rejoin again?
No, he's not able to hear. I
If
don't know
you
whether
have-
he's seeing the chats.
Chat would be more difficult for him, perhaps.
If you have his mobile number, you can.
No, we don't have.
So can we mail? If
Go
possible.
see the mail.
Very easy.
NC.
No, now his video is also gone.
Can you chat? Left the meeting. Will you join again?
Let us see.
So probably for the time being, you can stop sharing.
Okay, sir.
Just check if he has given any emails.
Yeah, he's saying that it is not working for him.
Oh, he sent email?
Ah,
Then maybe you can stop recording. Afterwards, we can restart.
talk with Parameswaran?
Yeah.
Yeah, hello. I mean, what is he getting at now? You can talk about the rational points on
No, whatever. I
most
don't.
curves. You can.
What I feel, even I wanted to ask, what I feel is usually when you take this, when you have a map and you look at the GCD of the multiplicities, then you can take a ramified cover and take the fiber product and normalization, that will be étal. But that will not be true when he takes the minimum. So
that is
minimum is somewhat surprising. Even I am waiting for that, what he gets into it. Yeah, the orbifold, what I have seen is this. They take the GCD.
What does he mean by modern way for what stacks or what? I don't understand. For orbifold curves.
Right,
So what is modern way for orbifold curves?
It's not clear to me in the arithmetic setting how he interprets. I don't know.
No, does he mean if you take say y square equals x cube?
Yeah.
That's a cubic equation. Is it? I think the arithmetic genus and the geometric genus. I'm using the old terminology of Walker and those.
Yeah, so I think my feeling is that what he gave that example exactly. See, when you go to x and y, when you get a étal cover, the geometry of the x and y is not changing. While when I come down on one side, on the y, it was a P1. But when I took the ramified cover, now it has become genus 2 curve. So that has only finitely many rational points.
Yeah.
So he is trying to say something about, though I moved from y to x, which has not much changed, but its geometry has completely changed because the base curve has suddenly become genus 2. And this comes out of the multiplicity of the fibers. See, when you look at the map from y to the base curve, P1, it had got multiple fibers and that is controlling the geometry. That seems to be what I could sort of understand. But still, it's not clear to me how does this minimum taking and does it become étal when I do the minimum? Only with the GCD that fiber product becomes and the normalization become étal. So I wanted to ask him this question, but
is he a friend of yours?
I knew him because we were together once. He came to ICTS and then he spent about close to a month in TIFR. He gave a few lectures.
He was at TIFR.
He was at TIFR about 3 years back.
He knows Professor Srinivas well, I think.
Yeah, he knows all of us well because he spent that much time here. Yeah. And he works on complex geometry.
Complex and arithmetic complex geometry.
Not much arithmetic.
Arithmetic, not too much. And arithmetic is giving interpretation, but his major works are all in pure complex geometry. I have not really seen much of his work in arithmetic. So it's essentially like function field. So he's saying something about how the fiber should behave. So I think his point is that though I made only étal cover upstairs between x and y, because I was forced to make a ramified cover from P1 to a genus 2 curve, that puts some arithmeticity.
Sham, I joined today.
Shyam is not our Shyam.
Hello, sir.
No, he worked on content.
No, not that person. Yes, I said Devendra. So he is trying actually from that place, but he's not able to make it probably. So we have to, he is saying that he will try once more and then we have to stop this meeting. He's probably old person, maybe in 75.
Oh.
Yeah.
So learning this new technology is a big thing now.
Yeah, true.
is a really big thing.
Yeah.
And especially these sudden changes, if something like this happens.
Then we are at loss.
Yeah, it's sometimes what Devendra just suggested, you just sign off and again sign in again, and it works sometimes. But
I mean, today anyway, there was no other choice because we couldn't hear anything. His video was there, but not audio. Suddenly it just went off. It was very sudden.
yeah, I think in our experience of this seminar for the whole year, this is the first time it has really, we are stuck.
Second time maybe once this person, because of networking,
Yeah.
Chaitanya, when he was giving talk.
Right.
Yeah, usually Sum is quite.
He is actually not expert of it otherwise, because he could not present the slides also by himself.
Yeah, I think somebody else is putting these slides for him.
That's right. Yeah.
Yeah, because you're always asking that.
Yeah. So he said he couldn't share it.
Yeah, do you want?
Professor, maybe we can finish. I will inform him.
Yeah. Anyway, you send him a mail. Ask him.
Yeah, so maybe you can announce as a chair to finish this meeting, and we will inform him.
Yeah. So, but is he trying? So, what is the status?
He was
from his side?
trying, but maybe we can wait for 2 minutes, but not. It is not working for him.
Okay.
He said that it is not working for him, so I suggested him to switch off the computer and then switch on the computer.
Oh my God. That's really.
No.
How are you?
Yeah, I'm fine. So, how are you? You're in Pune only, right?
Yeah, I'm at Pune. So you're still at TIFR?
Yeah.
Well, what is your retirement year or whatever?
It's supposed to be 60. Now I just got 2-year extension, so another 2 more years. So otherwise, I would have retired next month.
We get also extensions. So.
Yeah. Yeah, officially. Yeah, officially it will be now 2024.
No, he is asking about Professor Nitin Nisude.
Yeah, he retired about 2 years, close to 3 years back, more than 2 years ago. And I think he is probably somewhere in, he's visiting
Yeah.
IIT and so on. Yeah. Does Bhatwadekar come there often?
Hmm.
He comes, I think, frequently, Professor Bhatwadekar.
Oh, okay.
He guided a student here also for PhD.
Okay. That's good.
Yeah, I think, okay. Okay, so he's saying that it is not working.
Okay.
So maybe we can announce the news of this meeting.
Yeah. So anyway, there is no, even I wanted to ask some questions to him.
Yeah,
Since
maybe
we
we
lost
will
the
connect.
speaker.
Maybe on Thursday or Saturday you can put him. Or
No, it would be difficult because he is not very accustomed with technology. So troubling him again and again would be more cumbersome for him. So we can conversate with him maybe on email. I will put you people.
Yeah.
Convey your
So-
concerns.
Right. Anyway, you can share, whoever is around, you can share his email ID.
Yeah.
Ask him directly. I have some questions.
Or maybe he can send his whatever slides he has prepared to you, and you can give it up on that.
I'll have to go through. I'll check with him. I'll check. And I can try to see whether I can conclude, but I don't think I followed everything. So there is something is there. So I wanted to understand that part.
Okay, so because Professor Campana is not able to reconnect here for certain technical reasons, we have to end this meeting. And we will see again on the Thursday for Professor Noriko's talk. Pawan, maybe you stop the meeting on the YouTube, and then maybe you